Hello everyone. Today we are going to discuss addition theorem. The statement of addition theorem on probability, that is probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. Remember that whenever A and B are mutually exclusive, nothing but their intersection is empty. When they are mutually exclusive, that is A intersection B is empty, in that case, probability of A intersection B become 0. So, in this case, probability of A union B written as probability of A plus probability of B. And A comma B, suppose they are exhaustive events. Whenever they are exhaustive, that is union is empty set, union is not empty set, that is sample space. So probability of A union B become probability of sample space, that become 1. And also probability of A intersection B always less than or equal to probability of A, or we can say that probability of B, which is less than or equal to probability of A union B, less than or equal to probability of A plus probability of B, remember. Let us discuss some of the problems based on it. Suppose the question is, a fair dice is rolled only once. Find the probability of getting 8 or 10. The question is, a fair dice is rolled. Suppose that is rolled twice, not once, twice. Find the probability of getting 8 or 10. This is the question. Find the probability of getting total of those two numbers, 8 or 10. Yes. Suppose that A is the event such that total of those numbers is 8, and B is another event whose total is 10. Therefore, I can write here total 8 possible for 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2. Next, total 10 means 4, 6, one possibility, 6, 4, another possibility, and 5, 5, another possibility. Now, probability of A, favorable 1, 2, 3, 4, 5, divided by 36. Next, probability of B, favorable 3, remaining 36. Probability of A intersection B, there is no intersection, right? So that is empty, A intersection B, and hence probability becomes 0. Now getting 8 or 10, nothing but R indicates union symbol. Probability of A union B is the question. That is probability of A plus probability of B minus probability of A intersection B. That gives the result 5 by 36 plus 3 by 36 minus 0. That become 8 by 36. 2 2 ja, so 4 2 ja, 4 9 ja. Therefore, the probability become 2 by 9. Let us discuss another question. Suppose that a card is drawn from a pack of 52 cards. The question is, a card is drawn at random from a pack of well shuffled 52 cards, right? And given that event A, that is getting red color, drawn card should be red. And B is given that the card should be face card. Face card nothing but J, Q, K, right? Now, the question is find first one, probability of A. We know that probability of A equal to N of A divided by N of S. Total 52 cards in which only one card is drawn, 52C1. Next, red colored cards. A indicates the event of getting red card. Total there are 13 plus 13, 26 red colored cards. Therefore, 26 divided by 52, nothing but 1 by 2 is probability of A. Next, second one, probability of B. By the definition, probability of B equal to N of B divided by N of S. N of S is 52C1 and N of B, that is face card. Total how many faces are there? 4 into 3, 12 total. Why? Because heart, diamond, ace, JQK, 4 red, 8 red and 8 black will get, right? J, Q, K. J, Q, K. They are face cards. Next, red color, JQK, JQK. Heart, diamond. Similarly, black. Right? Total 12C1. Next question. Third one. Probability of A intersection B. Probability of A intersection B is nothing but that can be written as probability of A plus probability of B minus probability of A union B, right? Here we know the probability of A and probability of B values. Or otherwise, simply without using addition theorem, A intersection B is nothing but red and face. Red and face cards, total there are 6. JQK. total 6, right? So 6C1 in the numerator, 52C1 in the denominator part. Therefore, you can write 6 by 52. That is probability of A intersection B. Next one, probability of A union B. Now, probability of A union B by addition theorem, probability of A plus probability of B minus probability of A intersection B. Just now we got the results. Probability of A you got 26 by 52, probability of B 12 by 52, and probability of A intersection B is 6 by 12. It becomes 32 divided by 52. This one is the probability. Next, probability of A complement. That is probability of S minus probability of A, nothing but 1 minus probability of A. And hence here the solution is 1 minus 26 by 52 become again 26 by 52. Next, suppose the question B but not A. That is probability of B minus probability of A intersection B. We know that probability of B, that is 12 by 52 minus probability of A intersection B 6 by 12, 6 by 52, and hence final answer you will get 6 by 52. Next, suppose that probability of A intersection B whole complement is the question. That is 1 minus probability of A intersection B. And this is 1 minus 6 by 52. 52 minus 6 by 52. It become 46 divided by 52. This is the probability. Next, another question we will discuss. Suppose the question is A, B are two events such that probability of A 0.3 and probability of B, which is 0.1, and probability of A intersection B, that is 0.16. The question is, find the probability that exactly one event happens. This is the question. Exactly one happens, nothing but suppose this is A and this is B and this is sample space. Exactly one means this part as well as this part. Only exactly one. This is sample space, yes. Therefore, probability of exactly one event, nothing but from probability of A plus probability of B, you have to remove 2 times of probability of A intersection B. Probability of A in which one time intersection, in probability of B another time you have intersection here. So we have to neglect 2 times A intersection B part. Therefore, probability of A 0.3 plus 0.1 minus 2 times of 0.16. It becomes 0.4 minus 0.32. And hence it gives the result 0.08. Next question. Suppose that the question is the probability of at least one of A comma B occurs, given that probability of at least one event occurs, that is given as 0.6. Next, if capital A and capital B occurs simultaneously, its probability 0.2. Then the question is, find probability of A complement plus probability of B complement. At least one event is nothing but, in the figure, suppose this is A and this is B. At least one of AB is nothing but A union B part. Why? Because A consists only one. A intersection B part consists both. B consists only B, right? So the meaning of at least one is nothing but maybe one or two. Therefore, probability of A union B is given as 0.6 from this. Next, A and B occurs simultaneously. Nothing but probability of A intersection B occurs simultaneously, nothing but A and B. Probability of A intersection B, that is 0.2. Now the question is probability of A complement plus probability of B complement. Probability of A complement plus probability of B complement written as 1 minus probability of A plus 1 minus probability of B. Therefore, it becomes 2 minus P of A minus P of B. By addition theorem, probability of A intersection B or A union B, A union B probability equal to probability of A plus probability of B minus probability of A intersection B. Therefore, 0.6 equal to P of A plus P of B minus 0.2, and hence P of A plus P of B, which is 0.8. Therefore, you get 2 minus 0.8 in this case. That gives the result 1.2. Next, we'll discuss about conditional probability. Suppose the probability of occurrence of A when the event B has already occurred, that is known as conditional probability. Nothing but some condition is given. Conditional probability definition. The meaning here, occurrence of A when B occurred, that is conditional probability. Suppose that occurrence of A given that B already done, that is denoted by P given A. It is we can read as probability of A given B. B is already given. Based on that condition, you have to find probability of A in this case. So, symbolically, probability of A by B, that is probability of A given B, we have to read. And probability of A given B, that is defined by probability of A intersection B divided by probability of B. In case probability of B given A is given, numerator probability of A intersection B, denominator part probability of A. This is the basic definition of probability. Based on this, we will discuss some of the questions. Suppose that the question is, roll a fair dice twice. The question is, roll a fair dice twice. And let capital A be the event. That the sum of digits equal to 6. And assume that capital B is the event. Such that number come up twice. Same number come up twice. Now the question, what is probability of A given B? This is the question. Options are given 1 by 6, 5 by 36, 1 by 5, and none of these. Given that A is the event, sum of those digits is 6. Therefore, capital A is the set that containing pairs 1, 5, 2, 4, 3, 3, and 4, 2, 5, 1. Total there are 5 possibilities are there. Therefore, probability of A, favorable 5. Since fair dice rolled twice, denominator part become 36. So 5 by 36 is probability of A. Next, B is the event. Given that number come up twice, nothing but 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Total there are 6 favorable outcomes. Divided by 36 it is. Next, we know that here A intersection B, that is only one case, 3, 3. Now by the definition of conditional probability, probability of A given B written as probability of A intersection B divided by probability of B. Probability of A intersection B, from this only one favorable outcome out of 36 outcomes. So numerator 1 by 36, denominator 6 by 36, and hence it gives the result 1 by 6. Next, question. If two numbers appearing on dice are different, find the probability that question number 1, Sum is 6. Question number 2. One face is 1. These are the questions. The question is, two numbers appearing on dice are different. Right? Same numbers we got in the previous question, total 6. So that different numbers, nothing but you'll get 36, 30. Why? Because 36 minus 6, 30, right? Let us see. First, the event. Assume that B, two different numbers. Its probability of B equal to 30 by 36. Assume that A1, first question, sum is 6. Just now we got probability for this 5 by 6. Sum 6 probability 5 by 36, right? And their intersection, probability of B intersection A1. Only one having same number, remaining 4 are different. Therefore, intersection gives 4 by 36 probability. Now, probability of A1 given B, that is probability of A1 intersection B divided by probability of B. Probability of A1 intersection B, that is 4 by 36. Probability of B 30 divided by 36, and hence the answer 2 by 15. Next, on one face, the roll number is 1. So that here probability of A2 given B, probability of A2 intersection B divided by probability of B. We know that probability of B 30 by 36. And one face is 1 is given, and the other whatever. How many such exist is one face is 1 and the other 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Only one face, right? So reverse of this, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. Total 1, 2, 3, 4, 5 and 10. 10 by 36, which is probability of 10 by 36 is probability of A2. But the question is probability of A intersection A2 given B, right? The question is probability of one face is 1. B is given two different numbers. That is probability of B equal to 30 by 36. Two different numbers, right? And A2 is the event, one face 1 and the other different. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 3, 1, next 4, 1, 5, 1, 6, 1. Total how many are here? 10. Therefore, probability of A2 is 10 by 36. And probability of A2 given B, that is probability of A2 intersection B divided by probability of B, you have to write. And here, each and everything, if you observe, The digits are different. Therefore, intersection consists 10 elements. So 10 by 36 divided by probability of B, 30 by 36. It gives the result 1 by 3. Let us move to the next question. Application of this. Whenever probability of A given B equal to probability of A intersection B divided by probability of B, that implies probability of A intersection B written as probability of B, probability of A given B. Also probability of B given A. We know that probability of A intersection B divided by probability of A implies you can write probability of A intersection B as probability of A into probability of B given A. This is known as multiplication theorem. Just the application of conditional probability, this one. And generalized form, probability of A1 intersection A2 intersection A3 intersection A4 intersection and so on intersection AN. Suppose if you have, then probability of A1, probability of A2 by A1, probability of A3 by A1 A2, and so on you will get. Let us discuss question based on it. The question is, a bag contains 3 red and 3 green balls. Given that a bag contains 3 red and 3 green balls, 2 balls are drawn. 2 balls are drawn 1 by 1 without replacement is given the condition. Without replacement, 1 by 1 is drawn. Then the question is, probability of first ball red and second ball green. This is the question. Right? Given that the question, there is a bag the bag containing 3 red balls. 1, 2, 3. And it contains 3 green balls. 1, 2, 3. Now the probability that first ball should be red and second ball should be green. And here the condition, 2 balls are drawn 1 by 1 and the condition without replacement. First work, getting red ball probability. And then after getting red ball, you need green ball. So first I'm going to write red ball probability. Total there are 6, out of which only 1 by 1 is drawn. So 6C1, red 3, from which 1 ball is drawn. And work is not completed. Simultaneously, remaining you have 5 balls, right? Already 1 red ball is drawn. Therefore, from remaining 2 red balls, so that you will get in the denominator part 5. But now you need to draw a green colored ball. How many green are here? Total there are 3 green. So that 3C1 in the numerator part. 3C1 is 9. 6C1 into 5C1, 6 into 5, 30. That is, the solution is 3 divided by 10. Next. Suppose the question, 1 red and 1 green. Another question we will discuss. Suppose the question is, a bag contains 10 red balls and 5 yellow balls. 2 balls are drawn randomly 1 by 1 without replacement. Both balls red. The question is, bag containing 5 yellow colored balls and 10 red colored balls. 5 yellow and 10 red colored balls are there. 2 balls drawn at random. 2 balls drawn at random. Again, 1 by 1. The condition without replacement. The question is, both should be red. 1 by 1 we have to draw. First red, and after that again red from red. Already red color is drawn, and from that you have to draw red color without replacement. Total there are 15 balls, in which 1 by 1 ball is drawn first. To get red balls from 10, I am going to choose 1. Next, you will get 14 balls. Why? Because without replacement. 1 ball is drawn already. Again, now you have to draw red ball. Only 1 red ball is picked up, so that 9C1. This is the result. 10 into 9 divided by 15 into 14. 5 2 ja, 5 3 ja, 3 1 ja, 3 3 ja, 2 1 ja, 2 7 ja. Answer 3 divided by 7. Next question. The same, for which second one, at least 1 ball is red. The question is, at least 1 ball is red. Maybe 1 is red or 2 become red. That is the case. So that now probability to get first case red and second case red, both red. 1 chance is there. First case red, and in the second case yellow. Next, maybe first case itself yellow, and then second case may be red. At least 1 ball is red is given. Maybe both the times, or maybe first time or second time he may get red ball, right? Now, Out of 15 C1, one red ball, nothing but 10 C1. Again, without replacement, 9 C1 by 14 C1. Next, another case. 15 C1 in which red balls, 10 C1. Without replacement, so that 14 C1 here. Next, from yellow, we have to select one, 5 C1. Next here, 15 C1. First yellow, 5 C1. Without replacement, so that 14 C1. Now red from 10 C1. So this is the result. Next question. The question is, from a pack of 52 playing cards, 3 cards are drawn. 3 cards are drawn from pack of 52 cards. And that is one by one is drawn. And also without replacement. Next. The question is, find the probability that first and second cards, they are king cards, and third card is ace card. This is the question. The probability that first one king, second one king, but third one ace card. Total there are 52 C1, in which king card 4 C1. Next, one by one, so that now you have 51. Again, one more king card. Out of 4, 1 is drawn, so remaining 3 C1. Next, you get 50 C1 here. Ace cards, there are totally 4 ace cards, so that 4 C1. 4 into 3 into 4 divided by 52 into 51 into 50 you will get. Next, we will discuss dependent and independent events. Dependent and independent events. Suppose that A, B are 2 events, and A, B are said to be independent if occurrence or non-occurrence of one event does not affect the probability of occurrence or non-occurrence of other event. Occurrence of one event probability that does not affect probability of occurrence or non-occurrence. Occurrence or non-occurrence of other event is called independent events. Right? And by the definition of independent events, we can write probability of A intersection B as probability of A into probability of B. Actually, you have probability of A intersection B by multiplication theorem. Probability of A probability of B given A, right? Here, occurrence of B does not affect occurrence of A. So, there is no use of occurrence and non-occurrence of A, and hence simply you have to write probability of B. And also we know that probability of A intersection B is probability of B into probability of A given B also. Occurrence of AB does not affect the other. So simply this one you can write as probability of A. Both are same. Probability of A given B. Both are same. Why? Because occurrence of B does not affect probability of A. Simply you can write P of A. So that this is known as the condition for independent events. Probability of A intersection B equal to probability of A into probability of A. For example, there are two people. First one holding a normal dice and second one normal coin, right? Getting 6 on normal dice and getting head on the coin. One is does not depending upon the other, right? Why? Because one is dice and the other is coin. Getting 6, getting head. They are independent. This is the best example. Let us suppose there is a question based on that. Suppose capital A, which is equal to 1, 2, 3, and capital B, this is 3, 4. Capital C, 3, 4, 5. A and B are independent events. First question, given that A, B are independent, and given that probability of A 3 by 6, probability of B which is 2 by 6, and here probability of A intersection B 1 by 6, right? Now the question, find probability of A intersection B. Probability of A intersection B is actually probability of A into probability of B, right? So 3 by 6 into 2 by 6, that gives 1 by 6. And hence A, B are independent. This is the statement, correct statement, right? Next, just you have to write whether the given statements true or false. Second one is given that A and C are independent. Probability of A 3 by 6. Probability of C 3 by 6. This is 1 by 2 and this is also 1 by 2. Probability of A intersection C 2 by 6. Nothing but 1 by 3. Next, A intersection C, when they are independent, P of A must be equal to P of C. Here P of A 3 by 6. P of B C also 3 by 6. Therefore, 1 by 2, 1 by 2, 1 by 4. But here it is not coincide with 1 by 3. Therefore, it is false. A and C are dependent, not independent. Next, we will discuss Bayes' theorem. Bayes' theorem is also called as inverse probability. Let us suppose E1, E2, and so on, En. They are mutually exclusive and exhaustive events. All the N events are mutually exclusive and exhaustive events, in which event A, let capital A, that can occur with any of the events. Then probability of EI given A, that is written as probability of EI into probability of A given EI divided by summation probability of EI into probability of A given EI. This is the statement of Bayes' theorem. Let us suppose here mutually exclusive, exhaustive, nothing but their intersection must be empty as well as union must be sample space. Suppose this is E1 and this is En, E2, next E3, and so on. These are the events E1, E2, E3, and so on, En. And assume that A be any event, capital A. Next, probability of EI, that can be written probability of EY when it is given A. That is, finally we have tried favorable outcomes in the numerator, total outcomes in the denominator part. Suppose that the question is a bag contains 3 white and 2 black colored balls. 3 white and 2 black balls. And another bag B. Another bag B that contains 2 white and 2 black colored balls. Given that one ball is drawn at random from first bag A and transferred to B, and it is transferred to the bag B. One ball is selected at random from B and is found to be white. One ball is selected at random from B and is found to be white colored. Now the question is, find the probability that transformed ball is white. This is the question. Given that a bag that contains 3 white, 2 black, another bag contains 2 white and 2 black balls. Suppose that event E1 and E2. This is transferred ball, white. Next, transferred ball, black. These are the events, E1 and E2. And suppose that W, the ball which is drawn from B is white. Ball drawn from B, that should be white. Now I am going to write probability of E1 first. Transferred ball is white. That is, total there are 5 balls, right? In which there are 3 white balls, so that you will get 3 by 5. Next, probability of E2. Total there are 5 balls. When the transferred ball is black, here you have to write 2C1. Nothing but 2. 5C1 in the denominator part 5. This is probability of E1, probability of E2. Next, probability of E1 white, probability of E1 black. I am going to write probability drawn ball drawn from B is white. W I am going to write here. Drawn ball should be white. Okay. This is from E1 and this is from E2. Okay. Probability of W by E1, that is 3 by 5. Why? Because W intersection E1 divided by P of E1. P of E1 already 5C1. 3 by 5, and probability of W by E2, that is 2 by 5. Next, the question is, find the probability that transformed ball is white. E1 when transformed ball is white. This is the given condition. When the transformed ball is white, find the probability of transferred ball. That is the question. So that here you have to write P of E1, probability of W by E1 whole divided by both probability of E1, probability of W by E1. Next, probability of E2, probability of W by E2 you have to write. Therefore, what we get? In the numerator, you will get 3 by 5 into 3 by 5. First, these two. That is 9 by 5. Next, P of E1 into P of W by E1. 9 by 25. Here also 9 by 25, not 5. Next, plus probability of E2, probability of W by E2. That is 4 by 25. It gives the result 9 divided by 13. The question is, a bag containing 3 white balls and 2 black balls. Another ball B, bag B, another bag B that contains 2 white balls and 2 black balls. Here, one ball is drawn at random from A and transferred to B. You have to select one ball from this and you have to transfer to the second one. Right? One ball is selected at random from B and is found to be white. And after that, one ball is selected at random from B, that should be white. Yes, here, probability of E1, E2, I am going to select the events, transferred ball is white. Maybe in the transformation, maybe you will get transferred ball either white color or black color. So E1 transferred ball white, E2 transferred ball black. And assume that WB is the event, the ball drawn from B, that should be white, right? Now, P of E1, 3 by 5, P of E2, 2 by 5. Why? Because 3 white, 2 black. Next, after that, after transformation, now you have to select a white ball. So, probability of W by E1. Actually, there are four balls. When you select one ball, from A, then it contains 5 balls. So denominator part become 5. Now, since E1 is the white ball, this is white ball. Therefore, there are total 3 white balls now after transformation. So that in the numerator you have 3. In the second case, if drawn ball is black colored, B. Now there are 3 black, right? Total 5. So denominator part total 5. Black there are 3, but we are drawing white. So that only 2 you will get in the numerator part. And hence, by Bayes theorem, you will get the solution. First, in the numerator, you have to write favorable outcomes, and in the denominator part, you have to write total outcomes. Therefore, 9/13 is right answer. Thank you, Ananda.